6 PPD fix. All right, my name is Mary Borchitz. I'm with the City of Makotia. I'm going to be the moderator for this first session. With us, we have our presenters are going to be Jay Holtz. Jay is a professional engineer and a technical director for Oldcastle Infrastructure, Stormwater Group. He has over 35 years of engineering experience, with over 25 years primarily focused on stormwater treatment and storage. And then we're going to have Carla Milesi. Carla is with is the emerging stormwater technology coordinator with the Washington Stormwater Center at the University of Washington-Tacoma, the Center of Urban Waters. She's been there since 2014, and she has served as the lead scientist for the center, collaboration with the Department of Ecology on technical assessment protocols, so the TAPE program. Carla's going to start for us, and yeah.
Hello. So what we're going to do is Jay and I are going to be presenting together. I'm going to take the first half of it and talk about first of all, how many people here are familiar with TAPE, Washington State TAPE program? Okay, so most people. So I won't go into that too much, but TAPE added a new protocol, and I'm going to kind of talk about the background of that and the why and the what, and Jay is going to talk about the how, because they've already done a very similar assessment. And so for those not familiar, TAPE stands for the Technology Assistance Protocol - Ecology, and it's Washington State's way of evaluating and approving stormwater treatment technologies to be used on municipal projects to meet the municipal permit requirements. And it's been around. It was first thought about in 1999. It's been around since officially since 2002, and we've made updates along the way, including our most recent update, which was just completed last fall in November of 2024. And throughout the years since 2002, the main focus of TAPE has been on pollutant removal ability. Specifically, we focus on TSS, which is what we call basic treatment, and then looking at dissolved metals, dissolved zinc and copper, and total phosphorus. And the folks who are doing their assessment, they have to do testing in the field, and during their testing, they have to report hydraulic performance and all maintenance activities that occurred during their evaluation. But TAPE never had a formal process to assess maintenance requirements or to assess hydraulic performance, and we also didn't have any requirements for how long of a maintenance cycle they needed to meet, since it can vary so greatly between site and land use. So we would kind of get the data they submitted to us, but we had we didn't have a formal way of assessing it, and we didn't have any criteria. What we started seeing happening was, over the years, we would see folks coming in. This is the orange is the maintenance cycle that we would see from over the years, and this is based on a % water year. So starting back in 2004, all the way up to the most recent approvals in 2025. And the blue line is the hydraulic loading rate, the gallons per minute per square foot that these systems were approved at. And that is generally the way that TAPE approves systems, is they say this system is approved at 1 gallon per minute per square foot, and then they figure out how big they need to build it to accommodate all of the flow that would be coming into that site from their drainage area. And so over the years, we would see an increase in the request for a hydraulic loading rate. The manufacturers or the companies that were coming through the program and looking for approval were looking for higher and higher hydraulic loading rates, because that means they could build smaller and smaller systems, which would be great in some instances, because in the urban areas, we would like to have smaller and smaller systems. But often we would see a decrease in the maintenance cycles. And so some of these actually, some of these higher hydraulic loading rates that were requested, we didn't always approve at what they were requesting. So we did cut some of those back based on the data that we received. But we still were seeing a trend of a decrease in maintenance cycle and a trend of increasing hydraulic loading rates. And so really we started thinking about how we could go about managing that. So in 2019, we collaborated with we have a stakeholders advisory group made up of municipalities in Washington State and the city of Portland. We started collaborating with our stakeholders advisory group to figure out how we could address this. We then expanded that to work with we have a board of external reviewers made up of stormwater professionals from around the country. And we also engaged with the Stormwater Equipment Manufacturers Association to develop solutions and develop ideas of how we could update the protocol to address that. And we finished our protocol update in November of 2024. And so that's what I'm really going to focus on here. Most of those updates focus on ways to better confirm the hydraulic capacity and the maintenance requirements of approved devices. And so we updated requirements related to sampled flow rates, particle size, distribution analysis, effluent flow capacity, and then the one we're really going to focus on today is we added something called the post-GULD maintenance assessment. And a GULD, for those who don't know, is their general use level designation. And that is the certification that is given to a technology once that they are approved and can be installed in Washington State on these municipal projects. And so just going over the other updates quickly, sampled flow rates. And so over the years, we were seeing some systems that would have a couple of samples at the high flow rates, their design flow, but majority of the samples would be at 20% of their design flow, and we really didn't know how well these systems worked when they were kind of being stressed at their higher flow rates. And so we added a requirement that said that we needed a greater distribution of sampled flow rates for their evaluation. So now we are requiring that they have to collect 15 samples throughout their evaluation. 2 of those have to be collected at or above 100% of their design flow, 3 between 75 and 100%, 3 between 50 and 75%, and then the remaining 7 can be collected anywhere in that. But we really want to see how it works along all of the design flow rates, design flow rates. We require, TAPE has required since the very beginning for people who are doing the evaluation to test the influent particle size distribution. We know that the finer particles are harder to treat, and Ecology has said that the typical particle size in Washington State has an average D50 of 62.5 microns, which is pretty fine. So that means that on average, the majority of the particles in stormwater, they are expecting to be less than 62.5 microns. So for testing systems for approval, we want to test them with stormwater with particle sizes of a similar nature, because if it has a lot larger particles, it's likely going to do better, and we don't know how it's going to do when it's installed in more of a typical system with these finer particles. So we added some additional requirements for testing not only influent, but effluent particle size distribution. And if those particle sizes are not within what Ecology calls the Washington State range, then they have to do an additional statistical analysis looking at how it performs on those finer particles. And so we require them to kind of look at different bin sizes and then look at the treatment on those finer particles. We have not implemented this at all yet. Well, I shouldn't say that. There have been manufacturers who have done this willingly in the past. We have not implemented this as a requirement yet. And so we're still kind of finalizing what that is exactly going to look like, but we're hoping it'll give us some better data on those finer particles. We're also requiring that systems be maintained if they bypass at less than 80% of the design flow. We were seeing a lot of evaluations where the systems would bypass at these lower flow rates and they wouldn't be maintained. And so it didn't give us a true sense of what their maintenance cycle was. We might get information on when the maintenance was done, but not when it was needed. And so by requiring them to do the maintenance at a set point, should give us a better idea of what the actual maintenance cycle was during their tape testing. And so again, this is just during their tape evaluation. And then finally, we added the post-GULD maintenance assessment. And this is actually included in the tape guidance document. So if you go to the tape guidance document on the Ecology website, it is at the very end. It's after all the information about how the proponents or how the manufacturers needed to produce their final report. At the end, it talks about the requirements the protocol requirements for doing this post-GULD maintenance assessment. And this applies to all devices with a basic treatment general use level designation. So any device that has been approved for removal of TSS, and we call that basic because that is the bare minimum requirement for being installed for most municipal projects. They can add dissolved metals and total phosphorus on top of that, but at a minimum, they have to be able to show that they can treat for TSS and meet this basic treatment GULD. It was originally thought that we would only require it on new devices getting a GULD in the future, but Ecology has decided we are going to require it retroactively. So anybody with a current general use level designation will also have to do this testing. It is for the new technologies, they will have to do this assessment at 3 different sites. One has to be in the Pacific Northwest. The other 2 can be anywhere around the country. For people who already have their GULD, whether or not they have to do one, we decided if within their tape testing, if they were able to meet 30% of a water year and not need maintenance, a minimum of 30% of a water year, they only need to do 1 more evaluation. If they did not meet 30% of a water year during their tape testing, they then have to do 3 sites. And it's about a 50-50 split with our current GULDs, whether they have to do 1 or 3 tests. And the basic of the test is you have to assess how much of a water year you can treat before failing. And failing means bypassing at 95% of the design flow. And so essentially we want a system to go out and install, either install a new system, or if you have a system already in the ground, clean it, make sure it's maintained and clean, and then let it be online and let water flow through it for a full water year. And come out you can either do quarterly flow testing or continuous flow monitoring. Is that the end or is that 3? Yeah, okay. I'll be very quick. Sorry, Jay. So we can either do quarterly flow testing, and that is what Jay will talk about, or they can do continuous flow monitoring. And we want to know, at least on a quarterly basis, whether or not that system can still treat at their design flow. If they can, then they can leave, come back 3 months later, come back the next quarter and redo the testing generally the flow testing is done usually using either a hydrant, like in the photo, or using a flow truck. But we want to see how long the system can go and still be able to treat at the design flow without bypassing. If they bypass, they also have to collect influent samples for TSS and particle size distribution. They don't have to meet any requirements, but they have to just collect that data so that we can get an idea of, can give context to the maintenance data, knowing what the particle size was and how high the concentrations of TSS were. Once they're done with their tests, if the system fails, we want them to perform the necessary maintenance to bring the system back up to be able to treat at their design flow. And the reason for this is we want to be able to add all this to the general use level designation. And this is actually general use level designation for the BioPod that Jay will be talking about here. And it's kind of hard, sorry, it's kind of hard to read here, but front and center in the document, we have added a table that outlines when the testing was done, where the testing was done for their general use level designation testing for tape, and then when the maintenance assessment testing was done, and what % of a water year they were able to treat. And then further on in the findings of fact section of the document, we include the information about what maintenance was needed. And so we're hoping that this will allow municipalities have a better idea of how frequently the maintenance would need to be done, and also what kind of maintenance needed to be done, whether it was just simply scraping the mulch and replacing the mulch, or did they need to replace the entire media, so that municipalities can have a better idea of the maintenance requirements of these systems. And so I'm going to hand it over to Jay, and he's going to talk about the intricacies of doing the quarterly flow testing that they did for the BioPod.
Great.
And I'm going to
Thank you, Carla.
switch over to.
Oh, good. Thank you. I'm Jay Holtz, and I'm with Oldcastle. And so this will be a good opportunity now to show you what the program looks like when it's actually executed, because the BioPod was kind of the guinea pig for this program, so to speak. We tested the BioPod back in 2018. We got at the Ship Canal facility in Seattle, and the system performed great and met the GULD requirements for basic, enhanced, and nutrient treatment. But it didn't last very long because that's a tough site. And most, if not all, the systems that have been tested there have had a hard time with longevity. The great thing about the site is you've got all your pollutants there and you can show your system works, but how long it works was kind of a remaining question. We were the guinea pigs with the BioPod, and in the GULD it said, you know, that we needed to test it at a more typical site in Western Washington to see how long it lasted. And so there was no process for doing this. And so we worked, Dylan Ahern is here in the audience today, and Dylan and his team at Herrera developed a proposal for Ecology and said, you know, this is what we can do, this quarterly testing to show that the system, to determine how long the BioPod lasts in a more typical situation. So what I want to do today is, you know, talk about the BioPod biofilter so you know what it is, talk about our GULD approval and that stipulation, and then focus mostly on the hydraulic testing that occurred and then show the results. So here's the BioPod biofilter. As I mentioned, it has full GULD approval for basic, enhanced, and phosphorus treatment. It's a horizontal bed filter, so the flow then comes in on top of the media bed and goes down vertically through the media bed for treatment and then discharge. And it comes as a complete system. It is a high flow biofiltration media, so a smaller footprint is allowed, and or it allows for a smaller footprint for ultra-urban applications. Vegetation in this system is optional. I'm showing the planter box style biopod here. It's also available with a tree, and it has, since we tested it without vegetation, and it performs without vegetation as well as with vegetation. We're also allowed to eliminate the vegetation, put a door over it. You can also pipe flow into it with a deeper system. So that's the system, and our GULD approval outlined our treatment rate, which is 1.6 gallons per minute per square foot. So you take your water quality flow rate, divide by that 1.6 gallons per minute per square foot. That gives you the number of square feet you need. You select your system. The target maintenance for this system is 1 year. But as we all know, maintenance requirements are site specific because it depends on actual loading. You want to inspect your system. You know, that's kind of the bottom line here, is you want to inspect your system and do maintenance when it's required for each site. And you want to be prepared to do that. But testing like we did here can show what you can have in the way of expectations. So we did propose and perform the hydraulic testing that is largely the same as what Carla described as far as the updates in the tape are concerned. So first we identified a test site. We found a 4x6 biopod that was a surface unit. So basically it had a door on it. It had no vegetation, but it had a curb inlet, and it is in Des Moines, Washington. The design treatment rate for that particular system, and it's still out there operating today, is 33.4 GPM. It has a curb inlet, internal bypass. It's a roadway application, as you can see there in the photo. It had a pretty well-defined drainage area, Des Moines, Washington, and it was recently constructed. It had been in the field for about 8 months in operation. So the hydraulic test plan that Herrera proposed and was accepted was to determine the peak capacity of the system quarterly. And there was also periodic influent sampling that we needed to take to show that we were getting actual loadings. 10 grab samples for the influent, and then look at the TSS concentration from those grab samples. And then we also had to look at the TSS particle size distribution. That also involved paired effluent sampling for 5 grab samples of effluent sampling, actually, I screwed up my headings on this. I apologize, because we had to do TSS particle size distribution for the influent, and then and 10 influent samples, grab samples, where we looked at concentration and particle size distribution. And then 5 of those influent samples, we had to have paired effluent samples where we looked at concentration. So I got that. And then we had to report all that, of course. So here's the hydraulic test equipment. We've needed a fully maintained system. So it was like on day 1, and then 3 minutes, thank you. And then we had to have a water truck to supply water. There was no hydrant available, hoses to get the water to where we needed it, a flow monitor so that we know what the flow is coming into the system. We needed a diffuser and a dechlorinator because we didn't want chlorinated water going into the storm sewer system, the receiving waters. And we needed safety equipment, cones, personal safety equipment, etc. So the hydraulic test sequence was to prepare the system for observation. We wanted to go out there, open the lid, take a look around, fill the system to saturate the media, let the water sit in the system for 10 minutes or so, and then increase the flow to the point of bypass. So we put it right up to the internal bypass weir. We put the water surface elevation. And then we had to stabilize the flow. And that was a bit of a trick because we had a radio, and you have to radio back to the guy in the truck who has a valve, and he's turning the valve up and down and trying to stabilize it right at that bypass point. So we have the maximum amount of head, which is where you would need to get your water quality flow rate treated. And, a little bit more flow is allowed to go into bypass. So we stabilized it right there at the weir crest. And then we read and recorded the flow rate from the flow monitor. So that showed us whether or not we were meeting the peak hydraulic requirement for that system, which was 33.4 GPM. We just read and record the flow rate at that point and allow the system to drain and then demobilize. So it was pretty simple and straightforward. Here's the hydraulic test timeline. In September, late September of 2020, we maintained the system. So we had a fresh system to work with. Then we went out and did our initial hydraulic test in October. The first quarter was in January. That was our first active event where we were looking at the end of our first quarter. And then we had a second quarter in April, third quarter in July, and then the final quarter again in October. And then in the middle there, you'll see that there was a road sanding event. We had a big snowstorm. There were 9 inches of snow in Des Moines on February 14th, 2021. And they went out and sanded the road, and they never picked up the sand. And so all of that grit and the associated fines got into the system, and we went out there and looked at it, and it was just hammered. And so, we were waffled back and forth as, do we start over or do we see how it goes? So we ran out and we did an intermediate test there to see how things were going, and it was still meeting its water quality flow rate. And so it was like, well, let's just leave it and keep going. And that's what we did. But when the test ended, we decided to do some supplemental testing as well. So we did a 5th quarter and a 6th quarter. And the 6th quarter, we tested it before we maintained the system. And then we did a maintenance where we removed the mulch and 3 inches of media because it was holding a lot of sediment in the mulch and in that first 3 inches of media. We got it down to where it was relatively clean, and then replaced that, ran the test again, and showed that maintenance allowed the system to recover full capacity. So what did we learn? We learned that there's quite a range in TSS influent concentrations. I've got a table here where it shows that range. We had a high of 164 milligrams per liter. We had a low of 1 and a median of 23 milligrams per liter. So the concentration was somewhat low overall, but the apparent TSS loading was much, much higher. Again, you're taking grab samples, so they're snapshots. And we had a lot going on at the site that wasn't captured, but that in some of those pictures, you can see how heavily that system was loaded. The particle size distribution was low. You know, the D50 was 40 to 60 microns. And so that was right in line with the 62.5. Okay, I'll wrap it up here pretty quick. And where we did have influent and effluent paired samples, we had an 85% average TSS removal rate. So that was good to see the system was performing up to snuff. So I'm going to skip the table and go straight to the graph because it's a little easier to comprehend. So you can see the points that we have the design flow rate right here in the green line. Most of our points are over that. The last one, that's the fourth quarter out there that's below. And the dotted line there in blue, you know, is the statistical linear regression, which shows us that we got 115% of the water year at that particular site. So that was the end of the fourth quarter. Those 2 extra quarters took us through the winter or through the fall and into the winter. And so as it turns out, that last point that we took, we were at 80% of our design flow, which was where you need to maintain the system according to Ecology. And we had treated 270% of a water year because we had a very wet 2 quarters there. So, I mean, the bottom line is that an annual maintenance target is appropriate. The conclusions that we had after this was, you know, the test is reasonable to execute. It's pretty simple and straightforward compared to performance testing, certainly. It has a reasonable execution cost. The loading conditions can be very variable, though. You know, the numbers that come to you at the end aren't perfectly representative. They don't show you, you know, clearly we didn't see, you know, what any ramifications from that, either good or bad, from that sanding event that we experienced. So it does show that, you know, you really have to dig into it to find out what the intricacies are. A head-to-head comparison of systems will be difficult to make because, again, every site is different. So the bottom line here is that the actual maintenance cycle for any of these systems will remain site-specific, but I think that the testing that Ecology and the Washington Stormwater Center have introduced will go a long way toward giving people confidence in these systems and will help you to determine target maintenance cycles, and then you can look at each system individually after that. So, sorry I was rushing a bit there, but time is short. So thank you. We'll take questions now.
So the question is whether or not these are being maintained at the frequency that we see during no, I would say no. I mean, there are requirements within the permit of how frequently they need to be maintained, and my guess is that the municipalities don't have the ability to maintain them more frequently than they are required to do so. So that is one reason why we're trying to. We also have, it didn't really show up on my slide, but within the table that shows what kind of results they saw during their maintenance testing, we have a little footnote that says, we highly recommend that you take this into account when sizing your system. So maybe if a system needs to be maintained every 3 months, you would want to increase the size of that to get to your annual maintenance cycle. I understand that costs a lot more to install a larger system, but in the end, it might be less expensive than having to maintain it more frequently. So, but whether or not they're being maintained at the frequency that we saw required at least during some of the initial performance testing, I doubt it. And I do want to say a lot of the systems that we saw that had frequent maintenance requirements during performance testing were tested under a bridge, under the I-5 bridge, with very we don't know exactly what is going on with the water there, but it seems to gunk up the systems much more quickly than you otherwise would. I mean, it's great because it has all the pollutants in it and they're able to show performance, but they seem to gunk up the systems pretty quickly, so.
And you know, I will add, I think this shows that Ecology is looking at maintenance and, you know, I mean, you need to gather data and figure out where you're at before you begin to push things forward. We've all talked about maintenance for a long time and, you know, it's got to start sometime.
Thank you very much.